Okay, so I'd like to go ahead and get started just to make sure that we stay on track to begin with. I have just a couple of sort of introductory slides about sample and about today's meeting that I want to show really quick before Meetup starts off with her opener or her overview. So hopefully everybody can see my slides. Does this look okay?
Yes.
Okay. Great. And yeah, so this is a virtual workshop that we're having on the logP challenge that recently completed. And want to mention, that we especially appreciate the support of the NIH, which is now funding the sample challenges. So we're going to be able to be more organized with respect to how and when these are happening, and working on a real roadmap and have ongoing support for continuing data generation. This particular challenge, we especially appreciate support of Merck, which helped us do the experiments, and especially Meetup, who did those at Merck. So, as I mentioned, we now have funding from the NIH, and so we're planning more regular rolling challenges in 3 general areas: physical property prediction, host-guest binding, and eventually protein-ligand binding. And some of that's going to be continuing along the same lines that are familiar and have been part of the last several sample challenges, logP, pKa, those types of things. We're hoping to drive real progress in these areas, and then as we see that progress, move to sort of progressively more difficult challenges. Host-guest binding with experimental work from the Gibb and Isaacs labs is going to continue as their co-investigators on this sample grant, and then we're working to bring online some protein ligand binding challenges on carefully selected model systems. And we're also working on a partnership with an NIH institute called NCATS on some of that. And so in any case, I don't want to go too much into it here, but we already do have some SAMPL6 details specifically on the next host guest challenges up on our SAMPL6 GitHub repository. And we should have an overall roadmap for what you can expect the next few samples on our website, samplechallenges.github.io, very soon. And I also want to point out email is getting a bit more organized. We have an overall email list that's for anybody who wants news about anything about general sample related things. And you can join that using that link there. It's on our website. And then we'll also have a specific email list for each sample phase. So each sample number, like sample 6, sample 7, sample 8. Each sample phase will encompass multiple different challenges, but that's if you are involved in one phase and you may not want to be in on the others. You'll get, if you join one of those phase specific lists, you'll get emails just about that phase. And again, we still want to focus on sample, not to become a focus on winning. One of the key goals of sample from the beginning has been to ensure that we're encouraging people to learn as much as possible. So, in some sense, doing badly but learn a lot from it is preferable over doing well and not learning much. So we're after driving progress in the field. So that's part of the purpose of today's virtual workshop. We haven't done one quite like this before, where we have it timed pretty closely after the close of submissions. The goal really is not for people to discuss final polished analysis and really formal presentations, but more to talk about what they think so far about how they did, whether there's opportunities for synergy or follow-up, and sort of put people in a good place so that they can get as much as possible out of the challenge before writing up any papers for a JCMD special issue. And along those lines, JCMD has agreed to continue doing special issues and/or sections of the journal in support of sample, and we really appreciate that. So this is, on the right-hand side, is a cover from the last sample special issue. And anyway, so details for the next special issue are up online on GitHub and on our website, and the overall plan for those. And if you are writing up, please do acknowledge the sample NIH grant. The details are on the first slide for support of the experiments and overall support of running these challenges. So today's agenda, it's a hopefully a pretty informal workshop. There, people do have slides, but the intention is to allow a significant amount of time for discussion. Unless you ask me to hit pause during your presentation, everything will be recorded and then hopefully posted once I figure out how to do that. Each talk, we're trying to have it followed by questions and discussion, and there should be a slot for additional discussion at the end. Any questions on that part?
David, would you like to mention the last discussion part? What are we planning to do in the last?
Yeah, I think I don't have a formal agenda for that, but I think what I'd like to have happen is, people to brainstorm areas of like overlap or shared interest and possibly spin off groups that are going to be discussing that offline. But if there are other points that came up during the talks that we want to talk about, maybe issues with the data or things that we'd like to see in subsequent challenges, that could be part of the discussion too. Yeah, and since you're welcome, there's video, you can use video in this call. That is to say, if you want to speak and you want to let people see who you are, you can turn on your video. I'd encourage you to keep it off unless you're going to speak, just to ensure that we have the best quality of video of the presentation. And speaking of which, I can stop my sharing and start my video here. Maybe we can do, so we have 2 or 3 minutes, maybe we can do a quick round of introductions of just who is on here, and if you do have video, you're welcome to turn it on for that. So we could just go around and say your name and where you are. Mehtap, do you want to go first?
Hello, my name is Mehtap. I am at Memorial Sloan Kettering right now, working with John Codera's group.
Hi, I'm Marley Samways. I'm a PhD student in Southampton with John Essex.
Hello, I'm Tirupur Karsham. I am at the University.
I'll go because no one else is talking, but I'm in the David Mobley group and I'm helping to coordinate SAMPL.
Hi, my name is Christoph Loschen from Cosmologic, and I was participating in the SAMPL6 challenge in behalf of Cosmologic. Hi there.
Hi. This is Jim Huang. I used to work with Alex Bakel and Bernie Brooks' group, so I've been participating in a few sample tests. Now I have my own lab set in China, in Westlake University. So I'm having my own lab and starting to participate more in the sample test.
Yes, my name is Nicholas Tilka. I'm a PhD student in the lab of Professor Kast, and I participated also in the challenges in SAMPL5, so I'm excited for this webinar.
Okay. Hi, my name is Esteban. I'm professor in Chile, professor of chemistry, and it's my first time in the sample challenge.
Hi, this is Dorothy Lavorse. I'm at Merck & Company in Rahway, New Jersey, and I hosted Mehtap Ishik when she worked here.
Hi, my name is Caitlin Bannon. I'm also a graduate student with David Mobley and mostly just observing this challenge, but I've participated in the past.
Okay, did we get everybody who wants to speak up?
Well, so if you can hear me, my name's Andrew Paluch. I'm at Miami University, and I've participated in SAMPL5 and SAMPL6 now with my undergraduate students here.
All right, so I'm really excited about the cross-section of people and the world that we have here in this virtual workshop. So Mitap, do you want to go ahead and get going on your overview? You might be muted if you're talking. Got your slides.
Yes, correct. Okay, I'll start again.
Sorry, one more time. With your microphone.
But I'm talking to the speaker.
Yes, I have to disconnect this.
Can you hear me now?
Yes.
Okay. Today I will be talking about the structure of the SAMPL6 partition coefficient challenge, about the collection of experimental data, and I will be giving an overview of the evaluation of challenge results. SAMPL6 blind challenges. SAMPL6 blind challenges are a group of community blind challenges that are aimed for the progress of modeling methods for rational drug design. We address different medium difficulty problems and isolated challenges that would contribute to these modeling efforts, such as protein ligand binding affinities, host gas systems, and prediction of physical properties. In the past, there has been many years of hydration-free energy challenges, which improved the prediction of these values progressively. And then in 2006, SAMPL5, there was a distribution coefficient challenge, as we were running out of blind data that could be found for hydration-free energies. And in SAMPL6, we had a pKa prediction challenge as in the part 1, and part 2 we have partition coefficient challenges. Partition coefficient challenge which has just concluded. There has been special issues of each of these challenge phases, and there will be one for the partition coefficient as well. If I go over the roadmap of how we organize the challenges, is after the inception of the idea of having a test model system, the next stage is the experimental data collection. And then after data collection, the experimental data is kept blind for a certain time, and then we let blind predictions to be made, and we collect them before releasing the experimental data. And then we also share a performance evaluation comparing different methods. These are the stages that are completed so far, and we are now at the workshop stage where we get to discuss our results, and then publications will be gathered in a special journal issue. SAMPL6 logP challenge participants are encouraged to submit to Journal of Computer-Aided Molecular Design, and the submission deadline is September 15th. We expect publications from participants evaluating their own methods, and there will be an overall performance analysis paper written by the sample organizers, and a paper that explains the experimental data collection. Why did we decide to organize separate pKa and logP prediction challenges in SAMPL6? The rationale behind this comes from the previous logD challenge, where the cyclohexane water distribution coefficients were asked to predict. And when we evaluated results, we saw that the effect of ionization state predictions had a huge impact on cyclohexane water distribution coefficient predictions. One participating group, Pickard et al., published an analysis showing that how their QM-based logD predictions improved when they added contributions from pKa predictions. to it. So in sample 6, we had separate evaluation of our PK prediction abilities and partition coefficient prediction abilities. Partition coefficient refers to partition of the neutral substance between two phases, where distribution coefficient refers to both neutral and ionized species partitioning between in a biphasic system. So logP octanol water is the logarithm of the ratio of an analyte distributing between two phases. It's a proxy for predicting behavior of small molecules in biologically interesting environments, such as water-lipid membrane interfaces. For evaluating physical methods for predictions, it provides a test system for evaluating force field errors in protein ligand binding affinity prediction methods. Octanol is a hydrophobic environment, could be said to be similar to a protein environment. Methods that calculate solvation-free energies and transfer-free energies of a solid between two phases are similar to the ones where you would calculate partitioning of a ligand between aqueous phase to a protein binding phase. logP prediction allows separating force field accuracy from conformational sampling of a protein binding site or protein, and also it removes the effect of protonation state predictions from this physical property. Here you can see the relationship between the partition coefficient and the transfer free energy between two solvent systems for a solid. Properties of octanol phase are interesting. Octanol is a flexible molecule which would require a good sampling of conformational freedom around flexible rotatable bonds. Octanol phase is also wet, which means there's a significant fraction of water molecules in the octanol phase, which is measured experimentally as 27% molar ratio. And it's a heterogeneous environment that has hydrophobic and hydrophilic regions. As analyte, as a solute may prefer to partition to the hydrophilic regions or the hydrophobic tails of octanol assemblies. If I go into the structure of the SAMPL6 logP challenge, we ask the following values to be reported by participants. The logP, octanol water logP value, the standard error of the mean, which will capture the statistical error of a prediction method, and also the model uncertainty, which is the blindly predicted accuracy of a method. How well do you expect the predicted values to be close to experimental values? Participants were also asked to categorize their methods into physical, empirical, mixed, and other categories. And we asked for a detailed method description that should be publication quality. Some methods were very detailed in the submissions, some others were not. So if you have send us a submission file without too much detail, please contact again to provide more detail about your prediction method. Now I want to explain you how these experimental data was collected. I was hosted by Merck Pre-Formulation Group, which donated instrument time and their expertise as well as chemicals to collect these data. Dorothy Lavors and Timothy Rhodes, they guided me through these experiments. The instrument I used was a Series 3T3 automated titrator. And the measurement method we use for logP measurements is a potentiometric logP measurement method. There were 3 independent replicates of measurements for each molecule. Measurements were done at 25 degrees Celsius in ionic strength adjusted water and saturated octanol with water, and with automated acid-base titrations. This method relies on measurement of pKa. Therefore, you need molecules that have at least one titratable site. The pKa measurement method is potentiometric. And once you measure the pKa, you create different biphasic systems with different octanol water ratios and follow the apparent pKa shift to determine octanol water pKa. If I explain the potentiometric pKa measurements, it is while you titrate acid or base, you measure the pH at each step and the volume you use to come to this pH. And the potentiometric curve inflection points gives you the pKa of the system. Another way to look at this is to see what is the plot of buffering capacity changing with pH for this system. The maximum points of buffering capacity correspond to the inflection points, and you can measure the pKa of your buffering agent. Potentiometric logP measurements rely on detecting apparent pKa shift with respect to relative octanol water volumes in a biphasic system. The difficulty in this system is, in this measurement method, is determining the sequence of octanol water ratios that you need to measure. For example, this experiment was done at 20 microliters, 70 microliter, and 1,000 microliter octanol. And in each case, the pKa shifts. The equilibrium equations for the ionization and the partitioning are fit together to this data to measure the logP of the neutral compound. There were limitations and challenges of this potentiometric logP measurement method. Some of them we were able to overcome by optimizing the method. Some of them meant that we were not going to be able to measure logPs of some compounds. We started with the SAMPL6 pKa compound set, but only some compounds from that 24 molecule set were the ones that we were able to measure logP values of. So how to optimize the octanol water volume ratio? The more octanol you have, the more you will have a pKa shift, which is desired because you want to be able to resolve the apparent pKa points. So if you add less and the points are too close, you won't be able to measure it. But there's a limited flask volume, and then how much pKa shift response you will get is also determined on the logP of the compound. Measurable pKa range and the pKa shift was another limitation. Compounds had to have at least one titratable group, and we have to adjust the protocol to have a significant pKa shift. But we can only measure pKa's between 2 and 12. So if the shift is too much or it's getting out of range, then this measurement cannot be completed. And especially molecules with low basic pKa's that would shift in this direction, or high acidic pKa's that will shift in this direction, those are not suitable for this logP measurement. And how to optimize the concentration of the solute in the system. We want to dissolve as much solute as possible to get a high buffering capacity, buffer index above the buffering capacity of water. And this is tricky because then we have the problem of solubility of these solvents. So it was about finding an ideal concentration where it's high enough to catch the buffering capacity, but low enough that we don't have any thermodynamic or kinetic solubility issues. Another problem is, since we are titrating from low to high pH and neutral and charged states of the molecule that I've both visited, it is likely that you will observe a pH where the solubility of the compound is minimal. And this was one of the biggest limitations of this method. It eliminated many compounds from the SAMPL6 pKa list. Another problem was the limited option of organic solvent. We wanted to collect partition coefficients and not octanol. We thought that would be too difficult for a challenge for now. We wanted to collect cyclohexane or dodecaine logP values. But cyclohexane is too volatile in the system where the samples are left in an open vial. And dodecaine logP values seem to be out of range for these measurements. In the end, I was able to collect a logP data set of octanol water for 11 compounds. The chemical diversity in this set is somewhat limited. We have 6 molecules that have 4 aminoquinazolene group, and 2 molecules that have benzimidazole group. And this selection started from the kinase inhibitor fragment-like compounds that we selected for the pKa challenge, but then eliminated based on the limitations of potentiometric logP measurement methods. The values for pKa measurements in this data set have a narrow dynamic range, which is from about 2 to 4 logP units. Independent replicas were done on each compound, and the measurements are very precise. Here I'm also showing what assay type is used. Some molecules had kinetic solubility issues, which I had to overcome by pre-dosing some octanol before dissolving the compound in water. After the blind prediction phase of this challenge is over, we received a significant number of blind predictions covering a variety of methods. We collected 91 blind submissions from 27 groups, and these are from different method categories: 17 from empirical, 48 from physical methods, 17 mixed methods, and 9 methods that categorize themselves as other. How accurate were octanol water logP predictions in SAMPL6 challenge? So we calculated root mean square error, mean absolute error, mean error, and slope and R squared for these calculations, and confidence intervals were determined by bootstrapping. And you can find the statistics table in this link here. Because the dynamic range of the experiments were narrow, we think it's more suitable to use error metrics that are root mean square error or mean absolute error instead of correlation-based coefficients for this challenge. Let's look at the accuracy of methods that participated in SAMPL6 logP challenge. Here we are looking at the root mean square error versus method IDs across physical, empirical, mixed, and other methods. We have seen that 10 methods achieves lower root mean square error than 0.5 logP units, and the performance of these methods are indistinguishable based on the confidence intervals. And a significant number of submissions achieved errors less than 1 logP unit. And if I focus on the method that has the minimum root mean square error, which is the Cosmo-Term method, I can see that most of their predictions fall within 0.5 logP unit error, and only one molecule here that could be called maybe an outlier has a bigger than 0.5 logP unit error in these predictions. But is there reason to suspect some experimental error for SM13, which is the outlier here? To confirm that this molecule was the correct molecule that we thought it was, Dorothy Lewars did additional NMR and mass spectrometry measurements to confirm the structure of SM13. And also, if you look at absolute error versus molecules for the top 6 methods according to RMSE, you can see that there is no consistent absolute error that's higher for SM13 than others. So I think we can trust the SM13 experimental logP value. The accuracy we've seen in logP predictions of octanol water in SAMPL5. I would like to show a comparison to SAMPL5 prediction challenge. The system was different. It was a cyclohexane water system and a distribution coefficient prediction at pH 7.4. And the best methods that best performing methods achieve somewhere around 2.5 logP units error in the SAMPL5, where it is much lower for the SAMPL6 challenge. But some points to compare SAMPL5 to SAMPL6 is that in SAMPL6 logP challenge, we removed ionization and tautomerization state problems. They do not contribute to prediction errors. Ionization is removed because it's a partition coefficient, and tautomerization is removed because we looked at the structures and we don't expect automerization effects in this set. The chemical diversity of SAMPL6 dataset is more limited. Octanol is a more familiar solvent for partition coefficient predictions with lots of experimental data available. That's another contributing factor. On the negative side, heterogeneity of wet octanol phase is a bigger challenge for physical modeling methods. These are the methods that has the lowest RMSE. Overall, we see some physical methods performing very well, some empirical methods, global XBoost, local XBoost based QSPR methods, and some mixed methods at this range. If you look at the accuracy of empirical category, QSPR and random forest models seems to be doing well for this prediction set. And if you look at this spread of root mean square error for physical methods, some QM-based methods are top performing ones. And you can see here the physical method that's based on molecular mechanics that has the minimal root mean square error is molecular dynamics expanded ensembles method. It used amber OPLS force field. And the prediction accuracy of mixed category includes some QM methods followed by machine learning or QSPR-based training models for a correction in the end. And there's also a method here that used molecular dynamics features and then machine learning on these features to predict octanol water logPs. The other category includes junction tree neural network predictor and some QM-based methods. So far I've compared average error across method, average error between methods for all averaged over all molecules. Now I'm going to show a different view where I'm comparing the difficulty of predicting different molecules averaged over all the methods that predicted them. It seems that if I compare mean absolute error of each molecule, there is no molecule that's significantly harder than the other ones. It looks like an almost even spread of difficulty in these molecules. And if I separate this mean absolute error into different method categories, let's look at the physical predictions. Across physical predictions, it looks like an even spread of error for each molecule. The empirical predictions have a more fluctuating performance across molecules, which is as expected. You can also see a more detailed version of this analysis if you look at the violin plots provided in the sample repository that shows the distribution of errors for each molecule at this level. So far, I've talked about how accurate were the predictions. Now I would like to mention the model uncertainty and how are we going to evaluate model uncertainty predictions. This is the evaluation of how well did people predict their predictions will agree with the experiment or not. To evaluate if model uncertainty is overestimated or underestimated, we are using QQ plots, comparison to quantile plots of a normal distribution, and we calculate an error slope, which is going to tell us if the model uncertainty is overestimated or underestimated. So in this plot, the x-axis is the quantiles of a normal distribution, and the y-axis is fraction of predictions within range, which means QQ plots compare fraction of normal distribution within a specified number of standard deviations to the distribution of errors, which is the y-axis, the calculated value minus experimental value, distribution of errors that are within a certain number of the model uncertainty that it predicts. So if the model uncertainty prediction is very good, then the plot of these points should fall on the slope of 1, as the red line here shows. If the prediction has overestimated the model uncertainty, if the prediction is performing more accurately than the participant expected and reported as model uncertainty, and the fraction of their predictions that fall within their model uncertainty would be more than what they expected. Therefore, you would get a higher slope. If a participant underestimated on average the model uncertainty of their method, the fraction of predictions errors that fall within the model uncertainty that they reported will be less than what a normal distribution will have. Therefore, you will have a slope that is less than 1. So this quantity will be calling error slope, which is also being used in sample 4 and sample 6 challenges. QQ plots for each method can be found in this link. And if you would like to see the error slope values for each method and compare them, you can refer to the statistics PDF, which is also in the GitHub repository for SAMPL6. Here I'm showing 6 methods that were very good at predicting their model uncertainty as judged by the error slope, which are close to the value 1. I would like to finish with suggested directions for analysis of method performance. I know that after this workshop, people will be still working on the analysis of their methods and maybe working on publications. So here I will be presenting some suggestions for the analysis of method performance, and we can discuss these further afterwards if you have suggestions as well. The first one is, due to the limited dynamic range of this experimental data, we prefer to use root mean square error or mean absolute error over correlation statistics to judge model performance. Another question you can ask your data is, since we have a good representation of 4-aminoquinozoline containing compounds, you can ask, is your method able to capture the logP rank order of 4-aminoquinozoline series? Is it capable of capturing substituent effects of logP to logP? Another question is, are there any molecules with lower prediction accuracy than others for your method? Can you explain this from either the view of the chemical properties that they have or how your model works? Is bias or variance the limiting factor for the accuracy of your method? How does your method perform compared to similar methods in SAMPL6 challenge? To find similar methods, you could refer to the table of methods. It's under the analysis section, which you can see the categories of methods and as well as how they were named by their participants. Also, when relevant, we suggest pairing up to do comparative analysis and writing papers together. And if you would like to find who is the participant who have submitted a certain method, you can look at the user map in SAMPL6 report to reach one another. I would like to acknowledge the work of so many people who contributed to SAMPL6 logP challenge. Of course, the participants who did blind predictions and submitted us, as well as the organizers and advisors of SAMPL6, the 3R people who helped us, and the Merck reformulation group who made the experimental data collection possible by guiding me, and as well as funding. So in the next stages of the virtual workshop we're having today, we'll be listening presentations from a couple of participants. Andrew Paluch will be presenting, as well as Christoph Loschen, Nicolas Thielker, and Esteban Boringer Martinez. and Alexei Nikitin are the participants we will hear from today. Thanks for listening, and I'll be happy to have to receive questions now and also in the discussion stage later during the.
Yeah, we have about 10 minutes for questions and discussion, so please feel free.
David, we don't hear you.
You don't hear me? Okay.
I hear you.
I hear you.
Okay. Well, it could be an issue on Meetup's end, but yeah, so we have about 10 minutes for questions, discussion. Please fire away, and hopefully they'll have it. Can you hear me now, Meetup? Okay, good. Anybody? I will comment a couple of things really quick. One, this was something we began as, sort of long ago, actually, as in connection with the earlier PKA challenge. And in a way, this is the challenge we had been trying for, and then we spun that one off. So we are looking to do other future challenges along these lines, especially on other solvents. And so we're working to set up internships and things along the lines that will allow us to do that. But if people have connections or ideas for ways to get good data sets that deal with partitioning and distribution in PK, we certainly appreciate those.
I think one thing we've learned from this, and Mehtap can clarify or elaborate, is that this particular method of electrochemical titration and looking at shifts upon changing the fraction of the non-aqueous phase, because it requires solubility across the entire range of pHs, it really does restrict the number of compounds over the kinds of assays that we did last time for the miniaturized shake flask assays at Genentech, which use mass spec to detect the amount in partitioning in each phase. So I think a better approach we've learned is probably to return to that mass spec based method that can be easily automated.
More high throughput than this one. This one required individual protocol adjustment for each molecule. That one advantage of this method was most other methods measure primarily distribution coefficient. And if you can control your pH or the pH, then you can say, okay, now we go to logP. This method was able to measure logP directly, although it was very low throughput. I think we used it to our advantage, but for future data sets with bigger dynamic ranges.
Now that people can predict PKAs, as we've assessed in the last round of challenges, I think we can just go back to distribution coefficients instead of partitioning coefficients.
But people are better at predicting logPs than predicting PKAs.
Right, that's why we have to have them predict the whole thing.
More,
yeah.
I have a question concerning this pre-dosing concerning dynamic or kinetic solubility.
Yes.
Can you a bit elaborate on that, maybe?
Yes. So if I go to here, I'm picking the octanol volume versus water volume, and the way the regular data experiment works is first you add to your vial your weighed amount of powder compound, and an instrument dispenses the aqueous buffer, ionic strength adjusted water to it and dissolves the compound, and then it adds a volume of octanol to it, does the titration. When the titration is finished, it adds a little bit more octanol, does the titration, adds more octanol, does the titration. Sometimes the solid sample doesn't easily dissolve in the water phase before the addition of octanol. So in those cases, I was able to add the octanol first and then add water, and if required, add more octanol later. If there was a pre-dosing of octanol, that is to half the solubility of the compound, but that volume of pre-dosed octanol is included in the calculations of the volume of octanol to water. So it doesn't affect overall logP measurement. It's accounted for as a part of the volume of the octanol phase.
So it's just helping you achieve a different dynamic range.
Not really. It just helps to speed up the solution. Before the pH titration begins, I need all the analyte to be in the dissolved state, and that's what the pre-dosing is helping with. Because it could be faster kinetics to dissolve in octanol and then partition to water than try to dissolve in water and partition to octanol.
Okay, thank you.
We can make a comment on the way the prediction are judged using the mean average error. The range of the logP coefficient is actually very narrow. It's just 2 or 2.5 of logP.
Yes, it's only 2 orders of
Yeah.
magnitude.
So maybe one should also look to the person correlation coefficient carefully, because in some cases, for example, in MD-based physical prediction, OPLS and GAP for speed seem to have a bias error. They consistently overestimate all the logP coefficient, but the person coefficient is very good. Maybe it's even better than the SAMPL6, which performed well in the mean average error. So I do not think this metric is really it's really so significant. Maybe one should combine all the metrics. Also, the Kendall tau coefficients are important. Globally, the CGen, the charm potential, which performed very well for some prediction, but globally performed badly for the Kendall coefficient or the person coefficient. So one should try to find some kind of global mean to judge the results, so that one can learn as much as can, because candidate mean and unsigned error due to the narrow range can be somehow misleading, because if one paradoxically says that all the logP are around 3, one gets good mean and unsigned error. This is my point. So one should also look carefully to the person coefficient, to the Kendall coefficient, possibly delivering a combination of all these metrics to judge, to assess the performance of the various methodologies.
Yeah, I think in general, we like to not rely too much on any one metric, because usually the reality is there are issues with any single metric, and we also don't want people to pay too much attention to one metric, and nor do we want people to be too concerned about declaring overall victory, as opposed to focusing on what they can learn from the challenges. But I think you're right, there's value in Kendall tau.
We can add that to the statistics analysis, but it's hard to. I wish if we had a bigger dynamic range, it would be even more informative than it is now.
Sorry, I didn't get.
If we had a bigger dynamic range, I guess it would be.
Yes, it would have been definitely more informative. Then it would have been more meaningful to use the mean and unsigned error as leading methods. So one to learn something must see the results globally. For example, one important question was one important issue was the wet or dry octanol. I chose in my submission to use dry octanol, and I did so because I was not sure of the solubility of water if my model of water, the model of water which I used in my MD-based prediction, which is OPC3, was able to predict the solubility of water. What I observed in doing a simulation of water and octanol together in the 0.27 molar fraction, I saw clusters of water molecules. Is this correct? I really know. So I prefer to stick to dry octanol. Otherwise, I would probably introduce a systematic error which I could not control. So say, okay, I'm sure that I will, for certain, overestimate the logP coefficient, because octanol is more apolar than it should be. but at least I do not introduce any systematic error because of the failure of my water model, an octanol model, to mix correctly. Okay.
These kinds of questions would be fantastic to follow up on in your papers too. If you can explore systematically, maybe even for just a couple of compounds, what the effect of water is on your predictions. I know it's expensive, but it could be very
expensive. That is the point, because if you have cluster of water molecule in octanol, then you have to sample a lot, because if your solute by chance collides with this cluster, then you get totally wrong prediction. You get an erratic prediction. So I prefer to stick to dry octanol. This was done on purpose to avoid systematic errors.
We should go ahead and let Andrew get growing, since his time slot is starting, and then we can have more opportunity for discussion later. Andrew, you want to go ahead and share your screen? Andrew, are you there?
Yep, I'm here.
Okay, cool.
Hit the share screen.
Yeah, you're good.
Can you see it?
Yes.
All right, and you can hear me, Dave?
Yes.
All right, so perfect. My name's Andrew Paluch. I'm faculty in chemical, paper, and biomedical engineering at Miami University in Oxford, Ohio. And so I'll talk about some of my submissions, so in particular using some of the XMX solvation models. And then we also had a separate submission where we use linear solvation energy relationships. But in the time slot, unfortunately, won't have time to talk about that. And Dave, thanks for giving me the opportunity to talk. I've prepared an informal talk, hopefully not too informal, but thanks for allowing me to fit in too. We've got exams here, so this is perfect. So the entries I made, so on the left are all of the entries I made that use the SMX solvation models. And so the latest version of QChem that we have access to at the Ohio Supercomputing Center is now capable of SM12, SM8, and SMD, so we can do the whole gambit. And then also I have a series of LSCR predictions where I developed a group contribution method. So I have some smarts descriptors implemented in OpenBabel. We tried using the Azita fragmenter, and then UFC database, which is something online. Okay. And so kind of the top performing model, or the model that we had that did best, was this SM12 solvation trained. And so we'll talk about that. That was one of the ones that had an RMS error less than 0.5 log units. I think it was 0.49. And then, just using plain SM12, we were about 0.65. And so what I attempted to do, or the basic idea is, the standard approach to estimate log P using solvation free energies based on these methods would be to perform a solvation free energy calculation in neat octanol and neat water, and take the difference of that as an estimate of log P. Right? And so the basic assumptions here would be that the solute's infinitely dilute, there's no solute-solute interactions, and that water and octanol are completely immiscible. Right? So we wouldn't account for the solubility of water in that octanol phase. And so our basic idea was, we can readily crank out these calculations. What if we essentially take a hint from these LSCR types of approaches and instead treat our solvation-free energy in octanol and water as more of a molecular descriptor? So what if we take solvation in octanol, water...
Are you intending to still be on your first slide?
Oh, it shouldn't be on the first slide. So let me see.
I think we're seeing just your slide deck. Oh, there we go.
So let me go through this mode then instead of presentation mode.
Perfect. Thank you.
All right. Yeah, no, thank you. So, this is the next slide I kind of skimmed over. So, these were our entries. And so we'll talk about this SM12 trained model, which in that list based on RMS error was 7 out of the 91 entries. And so again, the basic idea was, if we were to perform these calculations as we did in sample 5, would be to perform a solvation-free energy calculation in octanol and water and take the difference between those two as an estimate of log P. Right? So assumptions would be solutes infinitely dilute and that our water and octanol phases are immiscible. And so, what we did is we said, well, what if we take these, instead of being, solvation-free energies, to be more representative of molecular descriptors? So trying to think of this as kind of a linear salvation energy relationship type of approach, where we have descriptors which account for specific behaviors of our molecule. And so what we did is we said, okay, we can readily calculate these values. What if we assume that log P is essentially a linear combination of these two descriptors? So essentially, we're going to do a multilinear regression where two descriptors are going to be salvation free energy in octanol and water. And so in order to do that, then we needed to, find a source of data to train on. And so what we came across was drugbank.ca. So drugbank.ca is a massive database that contains data for over 12,000 drugs. And for a lot of them, it contains experimental parameters such as logP and aqueous solubility. And so we sourced this drugbank.ca. And in terms of coming up with our data set, what we did is looking at the SAMPL6 molecules. And so I had a undergraduate student that, fortunately for me, very much likes organic chemistry. And so he pointed out to me that 6 of the molecules had the 4-amino quinzoline scaffold. And so what we did is we sourced the drug bank for similar compounds. And so when we first searched through drug bank just for molecules with that scaffold, we got thousands of hits. So then we further filtered it for compounds with available logP values, and then tried to look for molecules with similar sizes. And so pretty quickly, we were able to come up with a training set of 100 molecules from drug bank. And so the basic procedure then was we trained on that set of 100 molecules with experimental logPs. And then we also came up with an independent test and validation set. And so this is how we came up with our model accuracy. And so what we did for that is drug bank allows you to search their database for using similarity matching for reference compounds. So we were able to provide drug bank with the chemical structures for the SAMPL6 molecules and perform a similarity search for molecules with 0.5 or greater match. And so we also restricted that to approved drugs, which seemed to be all the ones with experimental logPs, and that resulted in 14 molecules. So then in terms of calculations, and so one thing I might not have mentioned is, so I'm a faculty in a non-PhD department, so I work with undergrads, and so kind of a goal in everything I do is to make things as simple as possible. So I like working with undergrads because I think of them as being, future process engineers. So the type of people we want to try and develop methods like this. And so kind of our procedure was we started with SMILES from drug bank. So drug bank for a given molecule, you can download canonical SMILES, and then the SMILES for SAMPL6. And so then using OpenBabel, we generated 3D structures using GAF and performed systematic conformational searches to identify the low energy conformer of our compounds. And then using QChem 5.1.2, we performed geometry optimizations at the MO6-2X CC-PVDZ level of theory and basis set, and then single point energy calculations in the SM12, SM8, and SMD continuum solvents, MO6-2X 631G star level of theory / basis sets. And so this essentially just came from, or why that is just from recent publications from the Kramer and Truller group, including some of their sample entries. All right, and so to be honest, part of me almost feels like we got lucky. And so the first plot here on the left is our logP predictions using SM12 versus our reference data. And so what I have here listed is direct and trained. So direct is actually the circles. My MATLAB legend's a little off. And then the X's are trained. So direct would be just directly taking differences in our dimensionless salvation-free energies and using that to estimate logP. And then the crosses would be our trained model, where essentially we're fitting those constants A, B, and C to minimize the deviation between our predicted and our model. All right, so we did a multilinear regression. And so, just looking at it, it doesn't seem to, well, there are noticeable differences between the two, but it doesn't seem to be hugely significant. And then same is true for the test set. Okay. And then when we make the sample predictions, right, which is this case, right, again, direct is the circles, and then the X's are our trained models, right? And so in terms of the RMS errors that were evaluated for us independently, this trained model had an error of about 0.49 log units, where direct calculations were 0.6. So it seemed, numerically it made a difference in terms of the overall error. But, just looking at it, to be honest, that's what you get. So in terms of a couple of possible sources of error, one of which we're trying to investigate for our publication is we didn't consider conformational dependencies of the molecules, right? So we just did this systematic search using OpenBabel, and essentially the justification was just as it's easy, right? And so in terms of giving instructions to an undergrad, it's relatively easy for them to perform the calculations on their own and to crank through things. We didn't play around with the theory or basis set at all. Presumably, that would have some small effect. So one thing we had thought about is in trying to think about these salvation-free energies as being more like molecular descriptors than salvation-free energies. We performed a series of calculations in which we were performing salvation-free energies in about a range of a dozen solvents, which included polar and nonpolar character. And our thought was to try and correlate things as a linear combination of these, but we've had some small issues with those. And then what we're trying to investigate right now is, as I said in that first step, we just took the smiles from SM12 and didn't really look at them and just cranked through the calculations. And then it was actually when we were doing the LSCR calculations, when we were cooking up these GC methods, we began to notice that hey, how do we treat HCl? And so in the smiles that were provided by sample, right, there's a dissociated HCl. And I am by no means a biochemist, nor have I ever taken a biochemistry class. And so, to be honest, I didn't know quite how to handle that. And so what we're working on right now is in molecule 9 and 12, repeating the calculations without that dissociated HCl and seeing if it makes a difference whatsoever. And then, a couple things we learned is, so SM12 was our top performing model. And so what was nice about QChem is we could do, single geometry optimization in vacuum. And then using the same exact structure, we could perform the calculations with SM12, SM8, and SMD simultaneously. And much to our surprise, especially for these larger molecules, there is quite a variation in the computed salvation-free energy using the 3 continuum salvation models. And so we look back at the Kramer and Truller papers, right? They do predict a variability in the 3, but the test sets they mostly looked at were rather small molecules. And so for the molecules we had here, it made a pretty large difference in terms of the actual salvation-free energies. And again, we didn't play around with different conformations. The other thing that we kind of need to work on is our choice of training set. And so the training set did seem to make a difference on our predictions, right? So even the differences were noticeable in terms of looking at untrained versus trained values. And so, one thing would be is in terms of, we didn't really investigate the accuracy of drug bank, right? So drug bank, you search for a molecule and it has data collected from all different types of sources. And so one question is, we never really evaluated the original source of the data from drug bank, or how much confidence we can have in that. And then the last point in terms of lessons learned is, we should look at the smiles before we just crank through the calculations, and then maybe think about what we do with something like this dissociated HCl before we run through the calculations. And so, the only last slide is in terms of acknowledgments. All the calculations were performed at the Ohio Supercomputing Center. And if you have any questions, you can send me an email. But with that, if you have any questions, you you're more than welcome to ask them. And thanks again for allowing me to talk today.
We have about 1 minute for questions, so not very much, but one maybe question or suggestion for follow-up is, have you looked at what would happen if you just submitted the value for the most similar compound from your training set, as opposed to training based on it? So like a simple null model that's just predict the value of your most similar training set molecule.
That I didn't think of. So I guess it would be a matter of identifying said molecules and doing the comparison. But that's certainly something we could do.
Yeah, you could do just a simple like Tanimoto similarity of some kind. Probably be a good null model to see if you can beat. We should probably go ahead and get Christoph up. But thanks again, Andrew, and his email is up there if anybody has more things they want to discuss with them. I know he has to drop off for work obligations.
Final exam time. Well, thank you so much, and I'll stop sharing now.
So can you see my first slide?
Yeah, that's great.
Yes.
It's not full screen, right?
It's not full screen, no. There we go.
Okay. So you can see it, right?
Yeah, you want to try advancing and make sure it advances okay?
Sorry?
You want to try to advance it and make sure it advances okay? Yeah, that's
that
good.
Works.
Yep.
Okay, perfect. Okay, so I'm going to talk about the predictions we made for the SAMPL6 logP challenge, and we made basically 2 submissions which were based on CosmoRS. And maybe I start with the first few words about myself. I'm Christoph Loschen. I'm a computational chemist, and I'm working in the group of Andreas Klamt at the company CosmoLogic in Leverkusen, Germany. And as you perhaps have noticed, we have been bought recently by BioVia, Dassault Systèmes. So currently there are a lot of changes undergoing at our small company here. That's also the reason why I have to leave after 2 hours of the workshop. So I'm sorry for that. But there will be enough time to go to this presentation. Okay, so it was quite interesting to see that such diverse kind of methods have been applied to this SAMPL6 logP blind challenge. And like QSBR, machine learning, deep learning, molecular dynamics, implicit salvation models, 3D rhythm, and also CosmoRS. And due to limited time, I will also okay, so this were our 2 submissions we made. So we were quite fortunate to be at the first and third position. I think in consideration of the small sample size, of course, this was also a bit lucky, to be honest. But nevertheless, we were quite content with that result. So due to limited amount of time, I'm just give a very short overview of the methods we have used. So you may know the CosmoRS approach, which was developed by Andreas Klamt, first when he was working at Bayer, and later he founded his company based on this method. And the basic idea behind CosmoRS, which is Cosmo for realistic salvation, is to use an implicit quantum chemical salvation model. Usually we use a BP86 functional for these surfaces, and then use this surface which is generated by the implicit salvation model to deal with intermolecular interactions. So this is a typical Cosmo solvation surface, and this is all kind of cartoon-like pictures here. But basically, we have surface segments on those molecules, and we make the assumption that those surface segments are the basis for interactions in solutions. And the main, or one of the main approximations, is that all interactions are possible. So every segment can interact with every segment here. This is an approximation which leads to quite efficient algorithms. In the end, we have intermolecular interactions which are of the typical kind, like electrostatics, which are based on basically the addition of those sigma surface segments. We have hydrogen bonds, which are proportional in their energy to products of sigma surface segments. We have van der Waals term, which is proportional to the area of the molecules, which comes from the Cosmo cavity. And we have also an entropic term, or combinatorial term, as it's termed in chemical engineering. And from those interactions, we basically make statistical thermodynamics, and in order to derive the chemical potentials in solution. A key quantity for this approach is the so-called sigma profile, which is just a collection of those charged surface segments, and you can visualize it, and it looks more or less like that. So here on the y-axis you have the amount of charge. On the x-axis you have the charge itself, and we collect all charges of the same size in a bin, so we get a kind of histogram. And then in the final interaction calculations, all those buckets with similar charge interact with the other buckets, if you say so. This is some example of a sigma profile on the right side. For example, you have here the sigma profile of hexane, which is rather inpolar. So you only have a peak in the middle and a neutral range. For more polar molecules like acetone, you have a peak on the here on the positive side, which is due to the fact that this is a screening charge, so the sign is inversed. This is sometimes leading to confusion, but the main charge on the oxygen on the acetone is in the Cosmo model is positive. Is something which one should remember. And for example, for water, which is the blue line here, we have an we have a donor peak here in the negative region, and we have an acceptor, a hydrogen bond acceptor peak here in the positive region. And this already gives kind of qualitative pictures of how molecules behave in solution. But in the end, we want to have numbers, and in particular chemical potentials, to derive properties from it. And an intermediate step is to get the so-called sigma potential, which is a chemical potential as a function of the surface segment charge. And this is shown here on this graph. We have again on the x-axis the charge of this surface segment, and on the y-axis there's now an energy, or chemical potentials to be more exact. And this gives you the amount of energy that is gained or has to be spent in order, which is related to the size of the charge density of the surface segment. And from this so-called sigma potential, which is averaged in an integral by the previously seen sigma profile, and also an entropic term. We get the final chemical potential of the solvent within of the solute within the solvent. And yeah, I'm just going to the workflow of how Cosmotherm works. With Cosmotherm is the implementation of the or the implementation by Andreas Klamt of the Cosmores approach. There are other implementations as well around. And so basically what we did with the sample molecules, we first did a conformational sampling on based on the SMILES which were given. We have a tool for that which is called CosmoConf, and is it's a kind of complex workflow where we start with structure generation with diverse molecules to generate diverse molecules with two tools, Balloon and RDKit. Then we iteratively reduce the number of conformers according to energy and cluster them according to structures. And also to we also do DFT calculations on those structures and reduce the number of molecules again based on chemical potentials with Cosmotherm. So here in this first step, there's already Cosmotherm involved to get the best set of conformers in the liquid state already. And usually a cascade of different density functional levels is used in order to be more efficient. So we start with a smaller basis set with a split valence basis set, and then we go to a triple zeta valence basis set. And then we usually have a conformational set of several molecules, and this set is then entering the Cosmotherm. And here we basically use the chemical potentials as calculated, as shown before, and we make also the assumption that we have some significant amount of mole fractions of water in the octanol, and with parameterization from 2019, usually every year we make a new parameterization, but we tested several ones from the years before. There were not so much a difference. And with the chemical potentials we have computed with Cosmotherm, we then get the octanol water partition coefficient. We just convert to the molar units, and then we have results. This was for our first submission. We made a second submission on a more efficient or somewhat more rough approach, which is based on or software which is called CosmoQuick. And the idea behind this is just to use a SMILES string as input, and then do the Cosmotherm calculation based on estimated sigma profiles. So what we do, we have a SMILES string as input. We have kind of cheminformatics backend which does bond perception. We do a normalization of structures. We compute circular fingerprints for those molecules, and then we go into a database of about 200,000 Cosmo files as computed by DFT, and use those previously computed fingerprints to find substructures which can make up the target molecule in the database. And from these fragments, we construct the Cosmo surface. And then after this step, the rest is basically as shown before. We can enter Cosmotherm, do computation of sigma potentials and do computation of liquid phase properties. For this competition, we have added on top of the Cosmotherm prediction an empirical correction term via machine learning. Here we trained on deviations from the experiment to have an additional term to correct for the some inaccuracies of the Cosmotherm approach. I will show this later in more detail. So for CosmoQuick, this shows how we do this sigma profile composition. Basically, I have mentioned already how we proceed here. So we go into the database, which is based on those previously calculated Cosmo DFT calculations and generate the sigma profiles. And beneath all of this, there is a kind of chemoinformatics backend to do the substructure and fragmentation approach. We introduce a kind of fragmentation error by this. If we compose those sigma surfaces by this chemoinformatics approach, which can be quite significant. But on the other hand, we have only a fraction of a second necessary for generating those sigma profiles. This is about the machine learning correction term we use for the second submission, for the CosmoQuick submission. So basically, we have in the first step, we use those approximated sigma profiles and do a Cosmotherm calculations to get a logP. And then we add on top of this a correction term, which has been trained on deviations from the experiment. As training and cross-validation data set, we have basically used the FISPROP database, and we have extracted from this training data sets via substructure search a test set of 37 molecules. Here are some of the descriptors we use for the machine learning correction, which is most dominantly the number of amino groups in the molecule. Then we have also number of conjugated bonds. This is the chemical potential of water as computed by Cosmotherm. And we have also here internal hydrogen bonds. This is the sigma moment, the third one, which is derived from the sigma profile. We have the chemical potential in the gas phase, rotatable bonds. This is the hydrogen bonding enthalpy. Again, a sigma moment from the sigma profile and the number of alkyl atoms. David, may I ask how much time I have left?
Yeah, you have maybe 2 or 3 more minutes for talking and then about 10 minutes for discussion, at least per the plan.
Okay, 2 more minutes, yeah, you say?
Yeah.
Okay, thank you. Good. So these are our results for the SAMPL6 prediction for Cosmotherm and for the CosmoQuick approach. There is a strong outlier for the SM13 molecule. I think Andrea started some discussion to check the experimental value. It's difficult probably to argue if this is an outlier, if our second method, for example, is much closer to the experiment. Currently I'm also looking what could have gone wrong in the calculations for this molecule, what could be an issue. But I have no good clue at the moment. So this is ongoing work. This is some study I did afterwards, analyzing our results. So here are our first two submissions. This is the Cosmotherm one in the first row and the CosmoQuick one in the second row. Then I used the Cosmo files without a fragmentation approach to and use this machine learning correction. So this is shown here with a slightly lower RMSE, and this is just a combination of the two methods having a lower RMSE. I think the main point from this is just to show that there is probably some room for improvement for the experimental methods. This is not an approach which we use or would deploy. It just shows that that there's also a significant influence of the fragmentation approach with the CosmoQuick approach. Okay, here one can see the two submissions plotted against each other, and here the two submissions with the CosmoQuick approach not using fragmented sigma profiles, but full Cosmo files, full DFT files, and the agreement is rather astonishingly good here, except for one compound, and this is a quite interesting finding actually. And yeah, so learnings for the SAMPL6 from the SAMPL6 challenge is especially for the first part, for the pKa part, was that we needed a systematic workflow for tautomer and deprotonation. We participated in the first part and did rather bad because we missed one specific protonation, I think deprotonation mode. So this is something we are working on right now. We tried also different parameterization, but the test set did show that there are systematic problems with this compounds class. Interestingly, this parameterization was used for the CosmoQuick approach. So the machine learning correction was able to improve on the systematic error. And yeah, as we have seen with the non-fragmentation approach, there is probably some more room for machine learning-based approaches on this kind of data set. And yeah, we also have to be careful to monitor this fragmentation error in CosmoQuick, which can be quite drastic. Okay, so finally, I would like to thank the organizers for this very nice challenge, and also for organizing this workshop and for giving me the opportunity to tell you something about our approaches. So thank you very much.
Thanks again. Are there questions for him?
Can I ask a question? Would you mind explaining a bit more how is the water modeled in your octanol phase?
Sorry, the water?
Yes.
Yeah. So with the Cosmo S approach, we use the sigma profiles, which come from the DFT Cosmo surface segments. And here we can also use sigma profiles of mixtures. So for a mixture, we basically take a mixture of two sigma profiles. So in this case, we take for the octanol phase, we take 27% of the sigma profile of water, and then the rest from the octanol sigma profile. So this is how mixtures can enter into the equations here.
Thank you.
What else?
Yes, I have a question on this kind of doing mixture using the molar fraction. Say that you mix according to the molar fraction, right?
Yeah, correctly.
Well, but in solvation energy, what is more important is the surface. So the volume fraction should be more important. Am I wrong? You don't overestimate the contribution of water by using the molar fraction instead of the volume fraction, because actually there is little water in octanol. The molar fraction is high, but since water is small compared to octanol, which is due, the volume fraction is much smaller, and this should be important for solution.
Yeah, right. But with the Cosmo-S approach, if we use we enter the molar fractions, but this is automatically converted into the right volume fractions in the approach. So it doesn't matter if you use a volume fraction or molar fractions. It is consistently taken into account.
Okay, thank you.
Anybody else? And for the record, because the Cosmo folks have participated a number of times, it's worth noting, I think, that they have typically been one of the well-performing methods. It's nice to see them keep coming back and also keep learning things from participating, even though they continue to do well.
Yeah, so thank you. For us, it's also kind of important, not being a commercial company, so we need something to show to our potential customers, and so this is actually quite important to us to show how predictive we are in real life situations.
Have you joined also the SAMPL6 challenge with cyclohexane? Do you have any comparisons between those?
I was not personally involved in the SAMPL6 challenge, but I think, yeah, there was also some issues about potential dimerizations and also about pKa values being missed, but yeah, the error bars were significantly higher there, right? About 2 log units.
Yeah.
So yeah, but I was not really involved in this kind of challenge. I know that we performed quite well there, but just relatively.
Yeah, that's my recollection as well, that challenge was difficult for everybody and that the Cosmos submission was one of the top ones. This is probably a good point to also mention a small change in how we're handling submissions, because it affects the Cosmo folks differently than it affects most others. So some people, sample historically has been, we have encouraged or been quite willing to have people submit multiple sets of predictions, because with the idea that will maximize how much people can learn, because then they're able to cross compare different methods without having to make sure that somebody else is running the method they might want to compare to. And in some cases, people will submit many different variations of a method or something along those lines. So occasionally folks who submit just one or a couple of sets of predictions have suggested that this is perhaps slightly unfair because some people are getting multiple shots on goal, if you will, or multiple attempts to do well, whereas others aren't. And so we're planning a change in how we handle submissions, in that we're still going to let people submit multiple submissions, but they'll have to designate one entry as their formal sort of competition entry or challenge entry. And those will be the ones that are ranked. We can still do comparison statistics for the others we expect, but so that people can submit multiple predictions for us to sort of verify that these were done in a blind manner, but there's still that people will have to select one of those multiple ones as their formal challenge entry. So we hope this will alleviate any concerns that people might unfairly benefit from getting to try multiple times while still preserving those benefits.
But one benefit is also when people submit multiple predictions, they can test different hypotheses about their prediction methods when they do. So we do encourage it still.
Yes. So it's not a change in.
Versions.
So it's not a change in what we take from people. It's just a change in how we rank things, and the idea that you'll need to formally designate one as your preferred submission. Okay, so I think we're ready to go on to Nicholas in. Do I have that? Yes, Nicholas in Stefan Kast's group.
Okay, so does the audio work?
Yes.
Okay, that's good. Then I'll try.
Yeah, we can see that.
I'll try and open it. So this works?
Yes.
Very good. Okay, so yes, I'd first also like to thank the organizers of this virtual workshop for giving me the opportunity to present my results here. And what we did to predict partition coefficients between water and octanol was to calculate the transfer free energy between those two solvents. And this we do by basically calculating the individual free energies of each molecule in both solvents. And to do that, we use the embedded cluster reference interaction site model, short ECRISM, which we also already used with varying success in SAMPL5 and the SAMPL6 pKa challenge especially. And to do that, we also have to, for example, do some conformational sampling, but there we basically stayed with the same methods we already used during the pKa challenge, which is why I don't want to talk about that today. It's already published. I mostly want to talk about the challenges with the solvent octanol and some things we learned from this challenge in particular. And ECRISM, not everybody might be familiar with this, so I just want to give a short introduction here. We basically use a quantum mechanical description of the solute and a 3D RISM, which is an integral equation theory description of the solvent around the solute. And these are calculated iteratively, so we can first use a normal quantum chemistry calculation, for example, using Gaussian or any other program. And we get the exact electrostatic potential in the vacuum phase. So to get the solvent effect, we use 3D RISM. We can use this electrostatic potential as input for a 3D RISM calculation, where the solute, other than the electrostatics, is basically described through a force field, in this case GAF. And the result of a 3D RISM calculation can be seen here on the right. It's basically the solvent distribution around the solute via the pair distribution functions, and we get thermodynamic quantities such as the excess chemical potential. And this solvent distribution around our solute can be translated for polar solvents such as water or octanol into background charges for another quantum chemistry calculation. And this is done iteratively, as I mentioned, until convergence. And then we assume we have, on the one side, our wave function of the molecule in solution, which gives us the quantum chemical energy, plus the 3D RISM excess chemical potential. And we call this our free energy G. And yeah, as I mentioned, we used this during the SAMPL6 pKa challenge to some success. There's just one problem, and that is if we just take the original free energies, they are typically significantly too high. And that is known deficiency of 3D RISM. It has nothing to do with the quantum chemistry part. And the reason is basically that the energy that is required to form the cavity in the undisturbed solvent is overestimated. But this overestimation is, of course, dependent on the solute's size, and that can be expressed via the partial molar volume. So we can use a simple linear regression model taking just the partial molar volume as and a free parameter, and we can get these corrected free energies. Here we trained with the Minnesota Solvation database, so these are solvation free energies in water, and those already give us quite good results. The additional parts for the charge are not really important here, because for the logP challenge only neutral species were considered. For details, please refer to the SAMPL6 paper, where we also had to deal with the ionized states. And our results for the SAMPL6 challenge were quite good. And that's why we decided, okay, we just use the exact same approach, just using octanol as a solvent. And there is one more thing which we had to consider for an octanol, and that is, as was already mentioned earlier, the water content. And we tested both dry and wet octanol. All the results I will show in the following are with wet octanol, because we actually saw it gives a small but significant improvement in our results. And we did the same training with just the partial molar volume term at first, but as we can see here, there is a clear deviation from the experimental values even after the correction. And ideally, the partial molar volume term should be sufficient, but here it does not appear to be. We do not know the reason for why yet, but for the time being, we then had to make do with a second parameter that directly scales the excess chemical potential. And then we get good agreement between experiment and calculated values. And we also submitted both 2-parameter and 1-parameter octanol results during the challenge. But again, as expected, the 2-parameter results were significantly better. So I will only show those results here. And this is our best result. It is wet octanol, 2 parameters for the octanol part, 1 effective parameter because all molecules were neutral for water. So only 3 free parameters were effectively used. And we did not have to do any further training with respect to experimental partition coefficients. So our RMSE was below 0.5. Our mean absolute error even 0.31. We were basically punished for this one very significant outlier, which is SM15. And that was quite surprising to us, because the related molecule SM14 is only missed by 0.53, which is still slightly above average, but not nearly as bad. And of course, that leads us to the question why it only differs in the alcoholic group and the amino group here. And so I wanted to look into why this particular molecule is predicted so badly by us. And well, it was not only us. I mean, it looks as though almost every group's estimates it's slightly lower, or at least in the mean. But of course, that's no excuse. We still can do better, I believe. But first, to do better, we have to find out what's the reason. And then in the Minnesota Solvation database, which we use as a training set for the individual hydration or solvation free energies, there are also transfer free energies between octanol and water. We did not use these as training. So here we just revisit them, and to our shock, actually, all alcohols, it does not matter if it's an aliphatic or an aromatic alcohol, they show this very similar deviation. And that's, of course, bad news on the one hand for our prediction, but good news maybe as modelers, so we can learn something about our model. And the first question is, of course, is this a result of a bad prediction of the free energy in water or in octanol, or maybe in both? And what I did first was to look at the other SAMPL6 results, because even in the pKa challenge, there were actually 2 more alcoholic pKa's that we had to predict. And yes, these are the actually molecules from the Minnesota Salvation Database, so they are not as complex as the one in the SAMPL6 challenge, but they still show the same behavior. Right, and for the pKa challenge, to, well, my relief, but also surprise, we actually found the alcohols were some of the best predicted molecules for our model. And even in the training set, there were some other simple aliphatic alcohols. There is no significantly bad results here. So it looks like alcohols are not always a problem for eSerism. At least for pKa's, we can, we already get good results. But for the logP, it seems to be an issue. So upon further investigation, I looked into the raw solvation-free energies in either water or octanol. And at first, when I plotted this for the first time, I was like, yeah, I don't see anything, because, okay, the octanol predictions are slightly too high, the water predictions slightly too low, and of course, if we then subtract them, we get a large error, but there does not seem to be some kind of correlation. One thing to note, maybe the octanol results are actually closer to the correct value for most molecules, and we already saw that for water we don't have a problem when we consider pKa. So these are a bit confusing, but when we actually plot just the errors for each individual molecule next to each other, then the picture becomes a little clearer. And the picture I think we can see here is that the error is not so much from any individual part from either the water or the octanol, because sometimes the water is better, sometimes the octanol is better, but the errors correlate very heavily to each other. So we basically always have the same distance between these 2 points. And yeah, that's where we are right now. So this is the next thing we have to investigate. Why is this so different for just alcohols, but not the other groups? But I think we basically only found this, this behavior due to the SAMPL6 challenge. So this was quite nice for us. And yeah, with this, I'd like to come to close. So we could successfully predict the experimental logP's with our best model to within 0.5 log units. We had to use an additional parameter in comparison with water for N-octanol to achieve good accuracy. The other, the two models where we only used one parameter, I think they had an RMSE of 1.2, 1.3, so they were not nearly as good. The wet N-octanol, I actually did not, I have the tables here in this talk, but I did not mention them, but they are consistently better, but yeah, only within like 0.1, 0.15 with the error metrics. And of course, the SAMPL6 workshop is always to learn more. So the first thing, obviously, we have to find out what is the issue here. Maybe we even have to go as far as to no longer use the GAF parameters for our 3D RISM calculations, because, well, GAF was not really made for 3D RISM. Maybe we have to use that as a starting point to parameterize our own force field, which would be possible, just somewhat time consuming. When we go further, as was already mentioned, towards distribution coefficients, well, we also have to take into account ions in the octanol phase. That is, yeah, another challenge that we would have to tackle once the challenge starts. And of course, we always have to look at in how far are actually, especially for the SM15, there seems to be a significant shift in just one direction. So why does every experimental, why does every theoretical model predict a slightly lower logP just for that molecule? Is there something that our physics do not capture? I think the experimental uncertainty was quite, was already mentioned. So these are our areas of investigation. And with that, I'd like to thank the organizers of the challenge and everyone who contributed to it, because only this way we can get further in developing our models. Thank you.
Thanks very much. Are there questions?
I may have a question. So if I remember correctly, you had one submission with a very high correlation coefficient, but also rather high error, MSE. Do you know what has gone wrong there, or have an explanation for that?
Do you mean by correlation coefficient the QQ plot that was shown earlier, or?
No, I mean the R squared. I think there was one submission of yours where you had a rather high R squared, but also a high error.
That might
actually had the highest R squared from all participants of this submission. I mean, okay, the range is not so large, considering it's just 2 log units, but I was just wondering what was gone wrong or right there.
So if it has a high error, it must be one of the one parameter models. I'm actually not sure what could be the reason for that. I mean, as I mentioned here, the dry and wet octanol, they are fairly close to each other always. And the one parameter octanol models are significantly worse. I could imagine that due to the fact that they are way off the diagonal here, that maybe it's just the description. So it's basically an artifact of how an R squared is calculated. But I'd have to look into it. Maybe it actually is that everything's closer together. But if it's one of the one parameter models, I don't think that it shows us that this model has actually good results. I don't think that.
Okay.
Well, what else? Anybody else? I'll just comment, Stefan, we should talk some stuff, and Nicholas, we should talk some when I'm there about the force field issues. Potentially there might be some ways we could help with that.
Oh yes, that'll be great, yeah.
So Esteban, you ready to get set up if Nicholas is ready to stop sharing?
Yep, I can do that.
How do you stop sharing?
It should be a stop sharing.
I see it. Thanks.
Okay, so I will try. Do you see the presentation?
Yes.
Okay, great. Oh, so hello everyone. Today I want to show the results we got for the sample challenge. This is joint work with Maximiliano Riquelme. He's a former PhD student from mine. He's now in the south of Chile as assistant professor, and he was visiting David Mobley for 1 year ago. So we had a quite naive approach to this sample challenge. We just wanted to see how good our atomic charges are performing, and all the work I will show is based basically on molecular dynamics simulations using force field with other atomic charges. And so I will firstly speak about the motivation, then about the methods we use, the atomic charges, show you some results and some corrections we think are enlightening, and then conclude at the end. So our motivation is basically to test the performance of atomic charges, which are derived from polarized QM electron density in different solvents. And previously, as I said, Maximiliano has worked with these atomic charges, and he looked at the free solve energy, the hydration free energies in the free solve database. And here that we published 1 year ago. On the left, you see basically the atomic charges, which we think are maybe a good candidate for force field developments. And on the right, these are the AM1 BCC results. And this is basically plot calculated versus experimental hydration free energies for 613 molecules in the free solve database. And basically, our results were we were happy with them, since we could, I would say, somehow get results which are similar to the AM1 BCC without any parameters, as I will show. So with these results, we thought, okay, if there's this sample challenge, let's see if the same atomic charges and the combinations we use can also be used for mixed solvents or other solvents in water. So before showing the results, I'd like to show you basically the methods, or how we obtained atomic charges and how we calculate the logP results. So as I said, atomic charges, they are derived from the molecular electron density. That means what we use is a method which is quite old, from 1977. It's called the Stockholder method. And basically what we use is molecular electron density. We get it from standard electronic structure calculations, with DFT, for example. And then this electron density is basically separated in atomic contributions, which are shown over here. How we do that is, or how Hirschfeld proposed it, was to use neutral pro-atoms, which are basically atoms which are positioned at the position in the molecule, and a pro-molecular electron density, which is just a superposition of all these atoms. So if you divide then how much each atom or pro-atom contributes to this pro-molecular density, you have something like a weight, which with you multiply the molecular electron density we got. So that is basically what is called a Stockholder, because basically you ask yourself how much does a certain atom contribute to the molecular density at a certain point. If you have then the density of the atom in the molecule, you integrate the density, then you get basically the charge. That is quite old, as I said, 1977, and the problem actually with this method is actually that it does not reproduce the molecular electrostatic potential. You get always too low charges, so it's not really useful for force field development. So some years ago, in 2016, Verstralen proposed, which is called the minimal basis iterative Stockholder method. So it's the same formula I showed you before. Again, you have a certain weight with which you multiply the molecular electron density to get the atomic density, and then you get the atomic charges. And how does it work is basically shown over here. So you assume that for each atom in your molecule, this is shown here for CO2, you for each valence in the atom, you have a Slater function with two parameters, which is basically the population and the width. And these two parameters you basically optimize, since in the sense that the density you get, this pro-molecular density I showed before, is as similar as possible as to the density you calculated from electronic structure calculation. And for this optimization, you use basically the Kuber-Gleibler divergence, which show the similarity between two different electron densities. So that was proposed by Verstralen, as I said, 2016. It's implemented in Horton 2.010, which is free to download, and it's interfaced with almost or many 3M codes, as for example Gaussian or Orca or whatever. So that was proposed by Verstralen. It works very nice, and it reproduces the molecular electrostatic potential in the gas phase of molecules. So in collaboration with Verstralen, then we included what is called, or what we think is a static polarization. What that means, very similar to what was shown in the previous talks. Basically, we include the electrostatic reaction field from the surrounding solvent, which could be altanol or solvent, calculated on a cavity surface. And there we use standard SN desolvation model in the Orca package to get basically the electron density now of the molecule, but the polarized electron density. And once we have this polarized electron density, we plug them in this Stockholder method, and we get basically what we call the SN-bis atomic charges. So this basically are charges which carry already the polarization of the surrounding solvent, and basically then interact in classic molecular dynamic simulations with standard force fields. So how do we get then the solvation hydration free energies? So basically it's standard alchemical free energy calculations. So this is the protocol we used. So we first generated the conformers with RDKit and optimized with this electronic structure method. Then we selected from this method basically the most stable conformer and did then state-of-the-art alchemical free energy calculation with Chromax. We used the SPCE water model and the TIP3P water model. For octanol, we used the Gauss force field. We estimated the free energy by the MBAR method. And this is important, yes, we add basically an extra correction for the free energy, which is the energy required to polarize the electron density. Since we work already with polarized atomic charges, you have an extra cost basically, which is to polarize the electron density from the gas phase into the solvent, which could be then octanol water. With that then, once we have the solvation and the hydration free energies, we calculate the logP with the formula I think you all know. So basically that is the way we got our results. And as I said, we were quite naive in our approach because we would want just to see how well these atomic charges behave and where we have to improve. So the results are shown over here. So these are the molecules which were in the sample challenge, and I will try to basically guide you through the main results. So basically what we did is we basically included two regions basically, which is a logP error of 1 unit and then 2 units, and what is beyond this 2 units. And the worst performer were these two molecules, SM13 and SM02, which, I will tell you then why we think maybe that they perform worse. So then we had these molecules I show you here in the violet regions, basically, and then the ones which were with an error of only 1 logP units is what are shown here in blue. There were 2 molecules, it's the SM08 and SM14, where we basically perform best in reproducing the results. So actually, we didn't thought that we will be very close to the experimental results, but we wanted to know how far we are, and we were surprised that we are not as far as we thought we could be. So we were quite happy. With respect to lessons learned, it was really tough for us by just looking at the structures of the molecules to get something like know if the structure or the functional groups in the molecule somehow reflect the deviation we have. There is kind of an error and knowledge we have from the hydration free energy calculations, and that's what I want to show afterwards. Just before I got then to the corrections which we proposed, basically is if you that's interesting actually for the people using or working in force development. If you just change the water model from TIP3P to SPCE, basically we saw that we get really worse in almost 1 logP unit. So the water model, at least for us, has a large influence on the results. That was quite interesting because we didn't thought that it would be so large. So now let me switch back and tell you something about the corrections. So as I said, we had some experience from this hydration free energy calculations, and there the data set was 613 molecules. So we had kind of statistics which we can use, or we thought we could use, to look a little bit closer at this logP results. So what we did is basically, and that was proposed in this paper, is basically we had for each functional group a correction, which we derive basically from this hydration free energy results. And basically this is all shown over here. This is a systematic error for each functional group, which is in the FreeSolve database on the hydration free energy. So what we thought is, okay, if we have these values basically for each functional group, we can take basically the results we have, we can take the structures of the molecules and then apply basically for each functional group there the correction to the hydration free energy. And that's actually what we do. For example, as I said, this is a secondary amine, so we we added this correction, and then also for the halogens, the chlorine, and then for the heterocycle, the other corrections. And then we basically recalculated log P value. So here we assume basically that we had no error in the octanol solvation-free energy, which is debatable, I would say. But so to our surprise, and that's what's shown here, is so stars are the corrected values and log P values is the usual one without correction. We got in most of the cases really closer to the experimental value. So for us, the lesson was that we have to, or the hydration-free energy may have a large influence on the results, so that there is something we have to work on. And in all cases, basically, we were getting better to the experimental results. So that, and we never, for example, got worse in the sense that we understood. So that's quite interesting. And in the sense that since the correction was based on functional groups alone, that means actually we can go back to the hydration-free energy results and look at these functional groups, how we can make them basically better. Just to finish up, so we also use other atomic charges, which are called the Hirschfeld-I charges, which are a little bit different, but the results we got from the hydration-free energy were also worse. So we thought they should be or deviate more, and in fact, that's what we see. So basically, the correlation is much worse than the MBIS charges, so that also correlates with the hydration-free energy results. But also here we see a quite big issue with the, or issue dependence on the water model. So that is basically the main message from our side. So our conclusion is, at least what we think is interesting, is that without having any parameters, basically, because in the sense that we don't fit our parameters to the results, we were really naive in just taking atomic charges from the electron density and then plug them into an existing force field. And at least I think we were not, or it's reasonable what we get out. So as I said, we're after transferable ab initio derived force fields, so we're not really experts in log P calculations, and our models basically don't include any adjustment to get them right. And just to finish up, and that was quite interesting, is after we finished, basically, Max had the idea of just looking at the SMD results without any molecular dynamics, without any force field. And basically, this is the results we got from B log def 2T triple tetravalence polarized results, and they're much better than the force field results. So, but again, I think I'm not an expert, but I think that the reason why you are much closer to the experimental results with this model is basically because this model we're trained basically for having right octanol and hydration-free energies, and then I would suspect that you will get also better results. As I said, we don't include any on experimental data when we, for example, derived atomic charges. So what's next for us? I think one thing which we are missing, and we are a little bit worried, is that we use the atomic charges from the electron density, but all other parameters from the force field are just taken from the GAP force field. So that is something we are a little bit worried about. And so the next step for us is to try to get the dispersion coefficients and the repulsive part of the Lennard-Jones potential basically directly from the electron density. That's something we plan working now, and we know how to do it. It's just a matter we have to do it. And I think the main lesson is that we have to basically go back to the hydration-free energies and see how we can get them better for the functional groups. And I think once we do that, I would guess that we'll also have better partition coefficients. And then, I mean, once we are there at one point, then we can go back and look at octanol solvation-free energies. I think that's something which is definitely on the list. And yeah, acknowledgements, I think, so this is the quantum chemistry and molecular modeling group in Concepcion. Max, as I said, is a former PhD student. He's now in the south of Chile. He did most of the work I've shown today. And yeah, I will also thank the collaborators, John Verstraeten, who is basically our main collaborators in the atomic charges, together with Paul Ayers and McMaster, and David Mobley also with the FreeSolve database and the hydration-free energies. It was really a nice collaboration we have. So with that, thank you very much for listening, and thank you very much the organizers for having to make this sample possible, and also to give me the possibility to share the results. And but not least, funding from the local agencies and the Max Planck Gesellschaft, or Max Planck Partner Group here in Chile. First. So thank you very much for your attention.
Thanks, Esteban. Are there questions for him?
Yes, I have a question. As far as I understood, you use two different sets of charges for the two solvents, right? Water and octane. Is that correct?
Could you repeat the question, please? It's hard to hear.
As far as I have understood, you used two different sets of atomic charges for the two different solvents, water and octanol. Is this correct?
This is correct, yes.
Okay. Then you said that you optimize one conformational state of each of these solid molecules.
Yeah.
Use this conformer to do the free energy perturbation calculation using Grover's. Okay, is this correct?
That's right. Yeah.
Well, I wonder if, first of all, I find very interesting the fact that you use two different sets of atomic charges, because it's the correct thing to do. The only thing that I wonder is actually some of these solutes have a conformational state, different conformational state, and they swap between these different conformational states. For example, they have Gaussian antistates, the amines as Gaussian antistates, which yields different solvation energy that must be reweighted by the free energy perturbation approach that is supposed to sample all this conformation with the correct Boltzmann weight. So I don't get exactly what you meant when you said that you use just one conformer. Because
okay, sorry, maybe I misspoke. So basically what we did is, so we first generated conformers just with the Rotamer library for each molecule, and then from this Rotamer library, basically we took the conformers and we did electronic structure calculation with the solvent water or octanol. Yes. And then we basically looked at all conformers we get, and from the conformers we selected basically the one which has the lowest energy.
The lowest.
So we did not take into account that we could have more than one conformer, at least for the beginning. So in the molecular dynamics, they could switch in between conformers, but we did not. The starting structure was just the lowest.
Oh, I know, but I mean, this should the free energy perturbation should take care of the switching between conformational states.
Yeah. In principle, if you simulate long enough, I would suspect that it should happen.
I'm telling this to you because this can be a source of error. I mean,
yeah,
do not sample correctly the conformance, you can get an error in the measure of this.
Yeah. Okay. Yeah. No, I agree. That's something we maybe we should go back and check. For example, if we sample the other conformers in the molecular dynamics simulations, which could be interesting. Yeah.
Any other questions for him?
I had a quick question. I'm just curious if you have intuition why this stockholder approach to dissecting the electron density into point charges works quite so well, because it seems like a ridiculously simple method to capture something like the electrostatic potential around the molecule.
So basically, the reason why it works so well is basically, I think, in the sense that so there are some issues, and I would say some, and we know where they are. For example, if you take nitrogen and oxygen, you have this free electron pairs basically, and we know basically that if you use atomic charges, you are not describing basically this local dipole moment at the atom. So that could be an issue which you would never get right by atomic charges, but that doesn't depend on your partitioning method. That's basically in your model inherently. So that's why that's something which we are thinking maybe to put in off-site charges basically to account for this local dipole moment. So with respect to the atomic charges, I think the reason why these atomic charges perform well, I think most of them is because we derive them from a polarized electron density. if you use the same partitioning method but with gas phase electron densities, we are completely off, and we have shown it for the hydration-free energies. So I think the most important thing is basically to include the polarization of the electron density when you calculate the charges. And that was done for the rest charges, but not by a solid model, but by using Hartree-Fock, which overpolarizes the electron density. So basically, you are counting somehow for something. I don't know if that answers the question.
Yes, thank you so much.
Okay.
Okay, so I think if you want to go ahead and relinquish sharing, we can have Alexei Nikitin speak.
Okay, yeah. Yeah, that's all.
Thank you. Alexei, are you there and ready?
Do you hear me?
Yeah, I hear you.
Okay, now I try my screen.
Okay,
yeah.
Yes, we do.
Okay, thank you. I'm Alexei Nikitin from Moscow Institute of Molecular Biology. I'm making calculations, PLO calculations with classical molecular dynamics using a alchemical approach. The method used here was calculation of free energy using expanded ensemble algorithm. About tools, first of all, I use a balloon automatic force field generator for making preliminary model, and WCM for quantum calculation, and a balloon program for molecular dynamics calculation on the GPU on the personal computers. About force field, the force field is under OPLS scheme. So potential derived charge on atom used. Lennard-Jones parameters was taken as usual by investigating the free enthalpy of operation and density of simple liquids. So using this scheme, the automatic force field generator generates the preliminary model that I used. After this, I made some manual adjustment from what I know about different functional group. In this picture, you can see the main point of manual editing. First of all, this was halogens. For the fluorine, I take parameters from our previous articles about perfluoroalkanes. For chlorine, I take parameters from my unpublished work, and most essentially, the hydrogen bonding parameters. This is my works on which I'm now going on. So in such way, I obtain the force field partly automatically generated, partly by my experience one. As this plot, you can see the results of obtained from these force fields. Root mean square deviation is not very bad here, but what we can see from this plot immediately, if you look at this side, you can see that all compounds that contain hydrogen, additional hydrogen bond group, all grouped on the right bottom side of this plot. So it's clearly that something wrong with the hydrogen bond here, and this should be a point for the further development. The next problem was the small model I used. I used only 32 octanol molecules for each models. I used, and it was octanol, mixed octanol and water simulation. 32 octanols is surely not enough, so that I made some tests. I calculate p-log value for benzamide. It was two calculations with 32 molecules and twice bigger models. As a result, we can see that the difference between these two calculations is half log units. So it's comparable with all precision of these calculations. So obvious, what I learned from this that I should use bigger models, as big as possible, and I should devote attention for further development of hydrogen bond force field. So thank you for your attention. In question.
Thank you. Any questions for him?
Would you like to comment about how you modeled the octanol layer? Were there water molecules in the octanol layer or just dry octanol layer?
Sorry, what octanol?
The octanol phase, was it dry in your model, or did you include water molecules in the octanol phase as well?
I always include water molecule. It was 32 octanol and 12 water molecules in every simulation.
Wet octanol. Wet.
Anything else for him?
Actually, can you also explain a bit further what was your observation about hydrogen bond parameters?
Sorry, I don't understand English well. Sorry, please repeat.
Sorry, you mentioned you would like to have further consideration of hydrogen bond parameters. What was your observation about the effect of hydrogen bond parameters in this set?
I simply seen that all substances with additional hydrogen bond like this one, like this one, they are all grouped on the right side. So this two try to be in water more than in octanol. So this I should have some disbalance with of hydrogen bond in this force field. But the hydrogen bond, this is the weakest point now, so that this is not finished job. I'm now working on it.
Thank you.
Okay, any last questions on that? If not, I think we can go ahead and open it up for general discussion or issues people want to revisit. I think just to recap, sort of we have some time from now until 10 if we need it to discuss any additional questions or discussion people have, and then potential connections or follow-up that should be done. I can also, if people want, give an update on some reference calculations we're running as a point of comparison. But any additional questions or discussion for the group?
One point I would like to revisit is the point about the counter-ions that were in the experiments and how do they affect the experimental logP values. Because that could be a curiosity. So in the experimental measurements, those counter-ions come from the solid crystals that the compounds we use, and when they dissolve in aqueous solvents, it should dissociate. It may have an effect on partition coefficient, but the experimental protocol we use has a property that minimizes this effect, which is we used ionic strength adjusted buffer, adjusted water for the aqueous phase, which means there is 150 millimolar potassium chloride already in the aqueous solution. So if a molecule has counter ions, counter chloride ions additional to that, it doesn't have a significant effect. So I was expecting people to either try to capture the effect of 150 millimolar potassium chloride in water phase, or ignore the effect of the additional chloride completely. Does anybody have questions about this?
Sounds like no comment on counterions. Does anybody who participated want to comment on whether they did or didn't include those?
I didn't include counterions for the same reasons why I use the dry. There could be sampling issues, including other errors. So I prefer to use dry octanol and no counterions.
Yeah.
So maybe I can comment on it. So we did not include counterions because our systems are so small that basically, or in the sense of number of water molecules and octanol, that I think you will end up in a sampling issue. But there might be a difference because, as I showed in the water model, which has two dielectric constants, could be that the water model, the ions change a little bit the dielectrics. So it might be important. But I think you need a larger box sizes and sampling.
Yes, definitely. Larger box size and sampling. You will be facing sampling issues, especially in measuring the logP using one single solid molecule in a big box of solid molecules and very different values. You may incur in serious issues.
I think one thing we should try to get out of this discussion is whether there are specific follow-ups that someone, not necessarily everybody, but maybe someone might want to take on as a follow-up experiment to assist with learning the most in the final wrap-up of the challenge. For example, if it were me doing these, I would probably think that I might want to run a molecule or a couple molecules at a much larger, in a bigger box with some counterions, maybe even at a larger than experimental ionic strength, just to ensure that there's a good number of them to help alleviate sampling problems, and then see how much it matters.
Yeah, ideally, it would be great to explore the two-dimensional axis of how much do counterions matter in the aqueous phase, how much water in the non-aqueous phase matters. To do some sensitivity analysis with a physical simulation-based method would be really cool.
So maybe so something we could actually do with 3D Risen is to adjust our solvent. So we had when we added water, we just added the parameters and did the 1D Risen calculation for that. And the same should in principle be possible for ions. One problem is that we have to do this training step on experimental data for hydration free energies and the solvation free energies in octanol. And when we add ions, can we really train on the same training data? That would be a question. I mean, we will get a difference. We will get a different result, but unless we can somehow validate or train our models anew, we can't really draw any conclusions from that. That might be a problem for us.
I wonder if that's a long-term argument for being able to train that type of thing to data from molecular simulations rather than experiment. In any case,
it's something that can be done, but
yeah,
we always hope we're better than molecular simulations. So I think for just 3D Risen, this might actually be sensible, but we already have the QM part, and so we might actually disrupt that.
Yeah.
It's kind of a difficult area, I think.
Yeah. In a way, this brings me back to the point someone made about, I think it was Esteban who pointed out that, the SMD solvation model does better on the logP calculations than their approach, probably in part because it's fairly highly fitted for water and for octanol, which is one reason why we in general find it appealing to not do to use solvents other than octanol, even if we also do use octanol for some of these challenges, because I think we want to be aware of differences in performance and limitations of methods that might require relatively a lot of training data. So I think what you're saying touches on something similar, that there can be methods that can work well in conditions that have an abundance of training data, but when they don't have that, things could be more challenging.
Yeah, basically yes. So I think it's always about the questions. I mean, if you just want to have the right logP value, then maybe implicit solvent and what we showed, what the other showed in the Cosmo calculations and so on are much more appropriate, right? But if for having a general force field where we want to also look at other stuff, then you have to go a little more physics-based with less parameters, and then it's hard to get right. I have maybe a follow-up question about the water content in the simulations. I don't know if there is a prior experience where it could matter most, because in principle we could do until August or something. It's just run some molecules with water and see if it would matter a little bit, and also the ions is something. I don't know how to, because we cannot do all with. I mean, that's a lot of combinatorics, but maybe there is some previous experience where you say, okay, look at this molecule that could be important. There the effects should be largest. That would be interesting to look at.
Yeah, I mean, as I said, I would want to do this type of sensitivity analysis for the water content in octanol and for counterions for several selected molecules. And I can't comment that much on whether people have done this for octanol. I will say that in one of the sample challenges, we looked at water content in cyclohexane, because it turns out there's a very, very small amount of water in cyclohexane, and it's extremely small. So we ended up putting in one water molecule in a big box of cyclohexane with one of the more polar solutes. And we also tried 2, 3, 4, 5, 6, and 7. And it turned out, regardless of how many water molecules we put in there, the solute gobbled them all up. And so they formed a little bubble around the solute molecule. Okay. Which I think gets at the point that in some solvents, at least, and cyclohexane is probably an extreme example, some compounds may be so polar that the local concentration of a co-solvent may be much, much higher than bulk.
Okay.
Yes.
I think Piro Pukaki has his hand up. I can't tell how to do it.
Actually, in this round, the logP sample round, there are several groups which tested wet octanol and dry octanol at the same time. They did multiple predictions. So there are means to evaluate the performance using exactly the same force field. And the differences are erratic. I mean, I think the priority should be on the force field rather than on dry or wet octanol or using counterions. These are much less important factors affecting the final values with respect to the force field parameterization. I mean, force field use the same set of charges for water and octanol. This is the weak point, in my view. Because of course charges are different. The mean charge on the solute are different in octanol because the octanol polarizes the molecule much less than water. And what struck me a lot in this logP sample round is the debacle of the polarizable force field, which were very bad, all of them. Actually, this is the correct physics because the solvent polarized the solvent, but the parameterization of the force field is the issue. I think that it's a long way to have a good, reliable, unique, say, parameterization describing this effect in these molecules. This is my feeling about this sample. The main issue is on the force field, rather than on this detailed wet or dry octanol or presence of counterions or not. If you use the eval method, you use a background plasma correction if the if the system is charged. And this is enough to get reasonable results instead of using few counter ions that provide the electromagnetic current. I mean, the main issue is force fields. These are not enough reliable. None of them, nor of OPLS, GAP, or the charm generator.
Is that do you have data that shows that in a way that you think is compelling, or is that, are you arguing that based on sort of?
No, I based this on the analysis that I did on MD-based results on this round of this sample 6 round. What strikes me is that none of the force field emerged as the best force field. I mean, for example, OPLS and GAP. Well, all of them are decent, I would say. None of them are terribly awful. But there are pros and cons in each of these force fields. There are shadows and lights in each of these force fields. For example, OPLS and GAP especially, they all overestimate the logP coefficient. And I think the main reason is in the fixed charge approach, which use the same charge for the solid in water and in alkaline. This is wrong, physically wrong, of course. So these points need to be addressed, in my opinion. The sad thing is that polarizable force fields are not doing any better, apparently. This is the sad thing. Polarizable force field, I mean, in the context of molecular dynamics simulation. What I expected in this round is the revenge of quantum mechanical approach based on implicit solvation model, because there you take into account the effect of the solvent directly on the electron density. And you exploit the fact that the solvent is an homogeneous medium. So you expect the results to be good. I expected quantum mechanics to be better than host-guest prediction. There, quantum mechanics was bad because the solvent there was non-homogeneous, like in this case, was an heterogeneous solvent in the bound state. So there was the host, and then there was the solvent. So this heterogeneity in the dielectric medium is a problem in quantum mechanics, is in implicit model of quantum mechanics. So I think that most of the effort should be devoted in developing better force field. Simple force field, but better force field in describing complex system.
Yeah, I mean, I think I agree with, significant aspects of what you're saying, although I'm also concerned that there could still be both sampling and convergence problems in some of these systems, and issues where we're not maybe dealing with important physical effects like adequately, like the amount of water in octanol or changes in local concentration. One other thing I've been going to say was that I know that octanol can form sort of, especially when wet, can form sort of micellar-like structures within it. And so there's the potential you could have solutes that are in like a very locally, let's say, hydrogen bond or hydroxyl-rich context, or placed locally in a very non-polar context, both in octanol. And it could take a long time for a solute in a molecular simulation to move between those environments. I haven't personally looked at these effects, but I know Michael Schertz had told me he'd done some work on this in graduate school and found that the results he got for calculations of solvation-free energies in octanol could be very, very dependent on the starting placement of his solute in the box, and because of these types of variations in environment.
Yes,
I don't know that was ever published, but I think something similar is probably been made.
I certainly agree with you, but the sampling issues can be somehow resolved simply by doing more accurate simulation, running longer FEP, using replica exchange, what is called solute tempering, all this stuff.
Yeah.
I mean, it's just a matter of using more time. I mean,
yeah. My question is whether anybody's done that in this challenge.
I did that, but you are supposed to do this, okay? But this is just a matter of investing computer time. Because you can do a simulation on octanol, which is a complex solvent. It is a slow solvent using a Hamiltonian replica exchange. Of course, you have to use many replicas to enhance the sampling. And it means you have to use a lot of computer time, but you can do that. I mean, this is just a matter, the conformational issue is just a matter of computer time. If you use non-equilibrium simulation like I did, you have to use many trajectories, and you have to use the replica exchange to sample the initial states, the end state. But this is just a matter of computer time.
Yeah,
Most
I agree.
not a matter of computer time. They are a matter of physics, and try to capture the essence of physics of this complex system without investing too much time. I mean, by leaving the description, the physical description at the simplest level as possible, because force fields are simple, okay? And they are nice, and from the point of view, and they perform decently, but they have to be better, I think. And most of the effort must be devoted in developing better, more transferable force fields, okay, which do not rely on training sets and so on and so forth. Use the physics of the molecule to provide parameters that works. Take into account polarization depending on the environment. I don't know how this can be done, but I think that this is the correct direction. Based technology that works in this.
I haven't gone carefully through the submissions yet, but one thing that I would be interested in knowing is whether methods that ostensibly use the same force field got the same answers.
No, they didn't. They did.
So yeah, I think that to me that says, well, as much as I agree with you that we need better force fields, and some of us are part of this open force field initiative that's trying to build some of those. I think that means that also we need progress on the other aspects of the calculation too. Otherwise, we'd be in a situation where the force field dictates the results.
Totally, definitely, totally right. I'm sure that you're right. There are actually few submissions which use the same force field, exactly the same force field, but were very different in the performance. And this is due reading the methodology they used, I think, to the computational time they invested in doing the calculator, because doing 5 nanoseconds per lambda state in a free energy perturbation approach in a molecule like SM02, which has Gaussian empty state, which interconverting maybe twice in 5 nanoseconds is simply wrong. You have to invest more time to do that. Otherwise, you will get a wrong free energy. Okay? Because, or you may get a correct free energy, but by chance. So the sampling issue is just a matter of computer time and of using the correct technology. The force field issue is a matter of physics. It's a much more complicated matter.
Yeah. Has anybody looked at the typical torsional interconversion times in some of these molecules with the typical force fields folks are using?
Maybe it's something that we can suggest to the people who used force field methods in their follow-up work as they're writing their papers.
Sorry, I didn't understand.
So if there's some of the molecules have multiple conformations, how long it takes the conformations to interconvert?
Well, also, it depends on the lambda states, of course. It depends on the if you use energy perturbation and you run an equilibrium simulation, say at a lambda state with a small coupling with a solvent, then the barriers are higher. So the events in going from one conformation to the other are more rare, of course, because there is no longer the screening of the solvent, because the molecules is like in the gas phase, and barriers get extremely high. I mean, several kcal. So, and if you sample in fact a conformation which is not relevant, for ionization free energy, then you get everything wrong, which is supposed not to be sampled, because you are stuck in a local minimum. Then of course you're wrong. But as I say, these are issues that are related just to the technology. We know that there are good technologies to bypass all these issues.
Yeah, I think I was thinking mostly about inherent interconversion timescales in solution phase, in octanol, and let's say in a non-interacting lambda value. Those should provide useful bounds for how long simulations are going to end up having to be.
Definitely.
Or
But,
even just knowing the barrier heights separating the.
well, the best thing to do is to run a preliminary Hamiltonian-Remlich exchange strongly and see how this conformational state are distributed. What is the Boltzmann weight compared to a standard molecular dynamics simulation? See if it gets right. If it doesn't, in 5 seconds, then you have to simulate it longer. Use a Hamiltonian ramp on each lambda states.
Yeah. So, of these issues we've brought up, are there any that particular people are going to be following up on themselves so that other people who are interested in knowing more about that can check in with them to find out what they're finding? But you mentioned, Hiro, you just mentioned the replica exchange type approach to assess some of the interconversion. Is that something that you're doing or you've done already?
Yes, I sampled I used a non-equilibrium approach where I need equilibrium sampling only at the end states, namely full coupling and in the gas phase. Well, doing an Hamiltonian replica exchange at the gas phase, you can do that on a laptop in 10 minutes because you have just one molecule. Okay? Harder, of course, for the other end states. If you start to decouple the solid from the fully coupled states, then it's hard because you have to sample the conformational states in a much bigger system, solid and many solvent molecules. It's costly from computational standpoint. In that case, you have to do at least 10 nanosecond simulation on 8 replicas to get it right, to get the good convergence on the conformational Gaussian anti-state, for example, for the amino compounds. So 10 nanosecond on 8 replica means 80 nanoseconds per compound for the fully coupled state when there is the salt. Of course, this time is much less when you simulate the molecule in the gas phase. Only one more. You can do that in a few minutes on lambda.
From that analysis, do you have any insight on which molecules undergo the slowest interconversions or which are the slowest degrees of freedom so that other people can check if they have sampling problems?
Well, the one which are connected by 2 rotable bonds, it's easy to see. Amino compounds and the most critical molecule from the sampling. But I also think that sampling problems in this round are less critical, much less critical than force field, because it's true that there are solvation free energy difference between these conformers, which might affect the final value. But I think that the error coming from the force field is much larger.
Yeah.
At least in my case, because I submitted multiple predictions done with the growth annihilation trajectory, with the Bennett acceptance, with both trajectory, bidirectional approach, and annihilation unidirectional approach. All these estimates were highly correlated, but the difference were much bigger between force field. I used 3 force field: charm, GAP, and OPLS, and the difference are striking in this case.
Yeah.
Much bigger difference between methodology, between variants of methodology, as it should be, in my opinion, as it should be.
Yeah, part of why I keep coming back to sampling so much is because you can imagine including this type of data in a force field parameterization effort if the calculations always give extremely or quite precise results given a particular force field, because then you can be sure that if you improve the force field, you should see improved results. But if you are applying a method that gives you disparate results depending on starting configuration or starting conformation or something, it's a lot harder to think about using it to improve a force field. So it sounds like you might have a protocol ironed out that is really doing adequate sampling, so it would make it more reasonable to include it in force field parameterization.
Well, I think that the roadmap for force-field parameterization should start from small molecules. We have to get rid of the sampling issue when we're trying to find the best parameters, for example, for chlorine, fibrosis, and so on. Because the hope is that once you have the decent parameters which are developed for small molecules, well, you don't have sampling issues. You have to be efficient to develop the force field. You cannot waste computer hours in sampling correctly states which are not relevant then for actually capturing the physics of the parameter you are trying to fix. So you have to stick to small molecules when you develop the force field. Then you can transfer these parameters to big molecule, and there you have to, in those cases, you have to address the sampling issues. You have to hope that this is the correct roadmap to use the data from a small system to large system. There are no other possibilities. I do not see any other viable possibility which is viable, which can be done.
Okay, so in our last few minutes, I know we've been talking a lot back and forth on this particular point, but are there other issues that people want to make sure get followed up on, or anybody who's gonna knows they're going to be exploring particular questions in follow-up work in case other people are interested in those?
Is it too early to discuss whether we want like the future of this particular line of experiments? David, is it too early to discuss, or do we have time reserved for that later?
We're in our last 10 minutes of this meeting, and I think it may be good to discuss that in person at the D3R workshop later this year when people have had a little more time to go through this.
I was just wondering if there was any immediate feedback about the challenge composition or the data type, or this versus the distribution coefficients, just in terms of planning for what people liked and what people didn't like.
Yeah, we could hear from people on that for a minute.
So first question is, do people prefer distribution or partition coefficients? Second question would be cyclohexane or octanol, or should we try for more diverse sets of solvents?
So from my point of view, I would like to have partition coefficients, because then I don't have to care about pKa prediction, which is an extra step basically. And this is quite challenging then, because you have anionic states which you have to describe correctly. So, but I think partition coefficient is good. And then maybe switching from octanol to other would be really interesting to see also other solvents.
We did learn that the pKa prediction is actually pretty good. It's not nearly as bad as I would have thought.
There were a lot of methods that did very badly, though. So there's some methods that are
definitely bad ways to do it, but there's
lots of pKas that predicted with 2 pK unit errors and a lot with 1 pK unit errors. So I think I'm concerned about those issues.
Yeah.
For example, if we calculated based on this partition coefficient challenge and the pKa challenge, there are common molecules. If we calculate what the logD predictions for them would be, the biggest contribution to error is going to be coming from the pKa. You will get something like 3 logP unit errors probably.
Yeah.
Also,
I think the plan was at some point to do a sample 7 with logDs with pKa's being provided, right?
Yeah.
So that boils down actually to a logP challenge, right?
Yeah.
So I'm wondering whether this really makes sense, because we now had the pKa challenge, we had the logP challenge, so why not simply repeating the sample 5 with a new data set, that meaning predicting logDs, including pKa's now.
But there is a difference. The difference is if you provide pKa's and ask for logD prediction, there are 2 things partitioning: the neutral species partitioning and the ionic species partitioning. In addition to the pKa prediction, which is handled with the provided value, you have to still predict the partitioning of the ion too, which, for example, this challenge did not include that. like a log P of the ion and log P of the neutral needed to be predicted.
That would be actually an argument for cyclohexane, because then the partitioning of the ions into the cyclohexane would be marginal, if at all. So
it would be negligible, yes.
Octanol would be a significant challenge in that way. Yeah. That's right.
Yeah, I mean, we've gotten some feedback from some folks, arguing that some of the challenges have been too hard because everybody does, or many people do very badly in some of them. I almost feel like the current challenge that we were just talking about today was essentially the right level of difficulty, and we might benefit from either an expanded log P challenge on a larger set with more diverse chemistry, or a log D challenge given pKa, because of the challenges that I think would still face us if we try to do both at the same time, like Esteban just mentioned.
From an experimental standpoint, does it make it easier to run a challenge if you're able to do log D with providing pKa? Experimental pKas, since there's more techniques?
You need to measure the pKas still, right?
And if it's a macroscopic pKa, it may not be directly informative of what species you're dealing with.
Right, it's not going to, we're never going to be able to get microscopic unless we can get NMR measurements.
Microscopic pKas are very difficult to measure.
It's possible we could find a set of compounds for which pKas and possibly even microscopic pKas are known, and then we could measure the log.
Or we could limit the set to molecules that have obviously one titratable site, then you don't have the microscopic problem.
Yeah. I guess the question was more, is there more or easier to measure experimental values?
Log Ds are much easier to measure. If we go back to the mass spec method, or Dorothy Labors has also mentioned some other alternative methods based on HPLC quantification. There's a variety of methods where we could do higher throughput log D measurements. The log P measurements are harder.
Maytap, do you want to mention the challenge we appear to be headed towards with GSK?
So with GSK, we are trying to collect log D distribution coefficient data with different solvents with the same molecules, which will probably include octanol too, but maybe also easier solvents as well. And there's also a possibility of collecting relative solvation-free energy.
Relative solubilities.
Solubilities, yes.
So this would be a particular compound set in a range of different solvents,
yes.
Potentially providing fodder for multiple challenges. Now, the timescales for that are not totally clear yet, but it's progressing slowly, at least.
Yes. And I think they will try to collect pKas as well, but they may not be very accurate pKas. It may be a crude experiment that determines the pK, as far as I know. For this challenge, I guess for evaluation and follow-up, some things that came up are looking at statistic Kendall's tau, in addition to the ones we have for now.
Yeah.
Other things we're following up on water content, also maybe ionic content in the phases, and box sizes. What else? Or maybe the transitions between the hydrophobic and hydrophilic phases of octanol phase, making sure sampling is long enough. I guess those are the follow-up points we came up with.
Yeah, I think we're doing some reference calculations here, which may address somewhat some of the finite concentration issues. We're also looking at some variations across water model, kind of like Esteban did, but not SBCE. We're going to do OPC and also look at force field differences between GAF and our Smirnov force field. It's not clear to me that we'll have human time to look in much detail at variations in environment in octanol, but we'll see how that works out. Well, we're coming up on...
anyone is planning to do some follow-up experiments, maybe if you tell us about it, and if someone else is trying to do the same thing, we can help to keep people in contact to do comparative analysis.
Yeah, or also if there's anything that you would especially like input from other participants on, like if you wonder if anybody has looked at X, we can try to get out. If you have questions you want us to send out to the participant list for you or something, we can do that. We want to ensure people are able to learn as much as possible from this. So we should wrap up there, but I really appreciate everybody participating, and please keep an eye on our samplechallenge.github.io webpage for additional updates. And then we have the SAMPL7 page, GitHub page, a repository is now online, and we're putting more stuff there in the coming days as well. So thank you everybody for joining, and I'll try to get this recording up online at some point.
Thanks for participating.
Thank you.
Bye.